Okay, so here's the Zoom meeting for Physics 231C. This is the Friday just before spring break. And we're studying this week Chapter 7. Chapters 1 through 6 were about general properties of motion. Kinematics, forces, the laws of motion, energy. Well, now we go on to the next few chapters, which are examples, specific examples of motion, which will apply all of these general concepts that we've been studying. So, as usual, read the chapter and take notes. Here are some of the equations that you have written in your notebook from reading the chapter. A mass on a spring will have two parameters. So you have say a mass here and a spring attached to the wall. There'll be two parameters, the mass of the spring and the spring constant or Hooke's constant. Now, as the spring oscillates back and forth around the equilibrium position, there'll be a certain frequency or a certain period of oscillation. And the angular frequency, so this quantity is called angular frequency, is the square root of k divided by m. The frequency is the angular frequency divided by 2 pi radians. So one cycle, which would be oscillation by back and forth, one oscillation back and forth from here to here, back to here, that would be one cycle. That would have a period equal to 1 over the frequency. And the frequency is omega divided by 2f, where omega is the square root of k over m. So this relates the time property of the oscillation to the mass and force parameters. Another example in the chapter is a simple pendulum, where you just have a pendulum swinging back and forth. There'll be two parameters, m, the mass of the bob, and L, the length of the string. And again, the frequency, or rather the angular frequency, is the square root of g over L, where g is the acceleration due to gravity. And interestingly enough, it doesn't depend on the mass. Well, that's pretty much because the force is proportional to the mass. And the acceleration is the force divided by the mass. So when you calculate the acceleration, the mass cancels out. This is an approximation valid for small oscillations. There's a section on energy for an oscillating system. So for example, again, if we consider a mass on a spring, so we have some spring constant K, mass M, and the mass is oscillating back and forth on a horizontal plane. There'll be two kinds of energy. There'll be the kinetic energy of the mass, that's 1/2 mv squared. And there'll be the potential energy of the spring, That's 1/2 kx squared. So these are results that we had from a previous chapter, really chapter 5, kinetic energy and potential energy. And energy is conserved. So this quantity is constant. So in particular, if the mass oscillates back and forth about the equilibrium between amplitude plus A and minus A, so 0 corresponds to, x equals 0 corresponds to the equilibrium position, and the mass oscillates back and forth between plus A and minus A, then if I evaluate the energy when it's at the maximum stretching or compression, that would be x equals A. At that instant, the speed is 0. So at that instant, when it's right here, its speed is 0. If I'm back here, its velocity is to the left, to the right. If I'm over here, the velocity is to the left. So it's going back and forth about the maximum displacement, that's the amplitude A, when the velocity is going from plus to negative. So at that particular instant, the velocity is 0. So the kinetic energy at that point is 0. The potential energy is 1/2 kA squared. And that relates V and X for any point in the oscillation. That's a conservation of energy. The simplest kind of oscillations are harmonic oscillations. And the equations for harmonic oscillations are written down in one of the sections. That's where the displacement x, the oscillating quantity, is sinusoidal. So it could be some amplitude A, cosine omega t, could be sine omega t, could be cosine omega t plus some phase. A simple case would be A cosine omega t. Again, omega is the angular frequency. So when t is 2 pi divided by omega, I have here the cosine of 2 pi radians. The cosine of 2 pi radians is 0. So, omega t x oscillates as omega t varies from 0 to 2 pi. That means t varies from 0 to 2 pi divided by omega. That's the position. Now the velocity, which has to satisfy this equation, is negative A omega sine omega t with the same frequency. So the velocity also oscillates with frequency omega out of phase with the position. So when the position is a maximum, the velocity will be 0. And when the position is 0, the velocity will be either plus or minus its maximum value, depending on whether it's going too larger or too small, going positive or going negative. And just as x of t leads to v of t, the rate of change of x, that leads to the rate of change of v of t, which is the acceleration. So you'll find this equation in that section. The acceleration is minus a omega squared cosine omega t. So the position and the acceleration are proportional. And that's because of Hooke's law. The force is equal to minus kx. So the minus sign comes. And then there's a more difficult section, section 7.6, on the processes of damping and resonance, where you have an oscillator, but there's friction. So it'll die out. Its oscillations will gradually die out. So that's an example of damping. Or if it's being driven by a harmonic force, then you'll have the largest amplitude when the frequency of the driving force is the same as the natural frequency. So that's called resonance. All right, so those are some of the things you'll need for the problems. Now let's take a look at some problems. Here's problem 744. The figure shows a model of a carbon dioxide molecule. Oscillations of carbon dioxide molecules in the atmosphere are responsible for infrared absorption, because if infrared light passes a molecule, it will set it into oscillation. That's energy, so there's a conversion of energy from the infrared light to the molecule. The infrared light will lose some of its energy, but then the molecule, or it could be visible light or ultraviolet light or whatever, but then the oscillation will produce additional infrared light, and that production of infrared light can lead to global warming. Now, one of the modes of oscillation is a symmetric mode, or actually, I guess it would be an anti-symmetric mode, where the carbon atom stays at rest and the oxygen atoms oscillate equal but opposite amounts in opposite directions. So the carbon dioxide molecule is shaped like a line. It'll be stretching and compressing, stretching and compressing. For that particular mode of oscillation, there are two other modes of oscillation, but for that particular mode of oscillation, the carbon atom is at rest, and the oxygen atoms, both of them, oscillate with equal frequencies. So as far as the motion of the oxygen atom is concerned, it's just like it's connected to a wall by a spring. So this binding of the two atoms can be treated as a spring with a spring constant K. The oxygen atom has a mass M1, and the end of the spring is at rest. So it's just like the oxygen atom is oscillating back and forth, attached by a spring to a wall. And so we know the angular frequency for that. That's the square root of K over M. We saw that on the previous page. So omega will be K over M. Now, what are you supposed to calculate here? So you're given K, you know M. M for an oxygen atom is 16 Daltons. (16 atomic mass units). You can look that up in the book or look it up at Google or something. So you put in K, you put in 16, you put in the conversion of Dalton to kilograms. So you got to convert this into standard units, which would be kilograms for a mass. And then you get M, you get omega, square root of K over M. Now what it asks is, what's the frequency? Well, omega is the angular frequency. So what's F? F is the angular frequency, which is radians per second, divided by 2 pi radians. One cycle is 2 pi radians. 2 pi radians, so one oscillation is 1 over 2 pi. No, one cycle is 2 pi radians. So if I take radians per second divided by 2 pi radians, I get inverse seconds, the frequency, hertz. So the unit there would be 1 over second, and we give that a special name for oscillations. We call that as hertz. So in a lot of the problems for this assignment, you'll have to express the answer in hertz. Hertz is 1 cycle per second. Here's another problem. This is a problem in the assignment, and it's also taken from the homework, problem 54. A piston oscillates vertically at a frequency F. So you could arrange that by this picture, this little mechanical system. You have a piston which moves up and down within a cylinder. I haven't shown the cylinder here, but there would be a cylinder here. And the piston just goes up and down within the cylinder. And the piston is attached to a rotating wheel. So as the wheel rotates, the piston goes up and down. If the wheel rotates with a constant angular velocity, then the piston goes up and down with angular frequency, the same as the revolution frequency of the rotating wheel. Now, find the maximum oscillation amplitude. So oscillation amplitude, that's A, such that a coin placed on the piston will remain in contact with the surface. So you want this thing to be oscillating up and down. There's a coin on the surface. Tommy, be quiet. And so you don't want the coin to come off the surface. Now, this will have harmonic oscillation. Omega or F. I guess you're given F. So you're given F and you want to determine A. Well, the vertical position of the coin will be A cosine omega t. There's the harmonic oscillation with frequency F. Omega is 2 pi F. So A varies between, Y varies between A and minus A, because cosine varies between +1 and -1. Cosine is an oscillating function that goes +1, -1, +1, -1, plus, minus, plus, minus. And so Y will do the same thing. Plus A, minus A, plus A, minus A, plus A, minus A. So the amplitude is A. That's what we're looking for. Now, I had those equations a minute ago. The velocity, the rate of change of Y, is minus A omega sine omega t. The acceleration, the rate of change of velocity, is minus A omega squared cosine omega t. So I have these equations from the section on harmonic oscillations. Now, the criterion for the coin to remain in contact with the piston is that there must be a force, a contact force, between the coin and the piston. If this is oscillating at, some speed with a large amplitude, the coin may fly off the top and no longer be in contact with the piston. Well, we don't want that. We want it to remain in contact with the surface. So that means there has to be a contact force between the piston and the coin. So for the coin to remain in contact with the piston, there must be a contact force. And when is the coin going to fly off? Well, it's going to fly off when the piston is at its maximum amplitude. If it's going to come off the surface, that's where it'll come off the surface. So we'll analyze it when it's at maximum amplitude. So the mass times the acceleration will be the force on the coin. That's the weight of the coin minus mg plus the contact force. And the contact force has to be greater than 1, greater than 0. The contact force has to be positive. If the contact force is 0 or negative, then the coin is no longer in contact with the head of the piston. So if we say that the contact force must be greater than 0, that means minus mg plus the contact force must be greater than minus mg. Now the m's will cancel. And we put in here A. A will be minus A omega squared. And when it's at its maximum, cosine omega t will be 1. So when y is equal to A, give the maximum upward displacement, then cosine omega t is 1. So omega t is 0, 2 pi, 4 pi, 6 pi, and so on. So A will be minus A omega squared. So I have minus A omega squared has to be greater than minus G, or in other words, A omega squared must be less than G. So that gives me a condition on A. A omega squared less than G. So the condition is that A must be less than G over omega squared. Omega is given. Well, F is given. But omega is just 2 pi times F. All right, so that's another example. That's an example of harmonic motion. Not from a spring, just from the contact force between the rod here and the piston. Let's look at another problem. Here's another problem which involves a pendulum. So there's a whole section in this chapter 7 about the pendulum. Simplest kind of pendulum is a mass on a string. So you have a mass M, a string of length L. You can measure the position with the angle theta. You may want to know the height, the bob will travel on a circular arc because the string has a constant length. So this will be circular arc from some maximum height to 0. We could call this y equals 0 at the bottom. Here's y, which will depend on theta. If I look at this picture, I see that y is equal to, so y is this distance. Put it in a different color. This distance is L cosine theta. And this distance from here to here, that's L. Because when the mass is at the bottom here, the length of the string is still L. So you see, L cosine theta plus y is equal to L. Or that is to say, y is L minus L cosine theta. So this is the way to relate the height of the bob, the height of the mass, by the angle theta. It's this trigonometric relation. Y is L minus L cosine theta. So, okay, so we always draw a picture first. So here's the picture, kind of like a picture I drew here. There's some maximum angle. I want a vertical coordinate, so I'll draw a y-axis for vertical. If I look at this little right triangle here, this is the side of the triangle adjacent to the angle. L is the hypotenuse. So this length is L cosine theta. This entire length is L. So this length is L minus L cosine theta. That's this equation. And so here's the picture, and now I write the equations. So what am I supposed to calculate? Energy, speed. I guess that's all, just A and B. There are two answers, A and B. So I want the total energy, so we'll call that E, and I want the maximum speed, so we'll call that V max. And what am I given? I'm given the length. So these are the givens. I already know these quantities. L, 0.9 meters. Theta max, that's 32 degrees. M, that's the mass of the bob. We always assume that the mass of the string can be neglected. The bob is much more massive than the string, so the string is unimportant. You can neglect that, but M is 0.41. So these are givens. I have conservation of energy, 1/2 mv squared plus mgy is constant. So that's the kinetic energy and the gravitational potential energy of the mass. That energy is equal to 1/2 mv max squared, because the maximum speed will be where y is equal to 0. So as this comes down, it's gaining speed until this point, where it'll have the maximum speed. No, when it's coming down, yeah, when it's coming down, the speed is increasing. Then when it goes on the other side, the speed will be decreasing. But when it's coming down, exactly at y equals 0, at that instant is when it has the maximum speed. So if I apply this equation again, this same energy is equal to 1/2 mv max squared plus 0. These two energies are the same by conservation of energy. And I can also calculate the energy at this point. At that point, at that instant, the speed is 0, because it's coming up, it's slowing down, slowing down, slowing down, slowing down until it reaches this point, it's at rest. At that instant, it won't be moving. And then it'll fall back down again. So here, the velocity is increasing, velocity is positive. Here, the velocity is decreasing, so the velocity is negative. Right here, the velocity is neither positive nor negative, it's 0. So again, if I calculate the energy again, at the point where the velocity is 0, the energy would just be mg y max. And that y max is L minus L cosine theta max. So this is the constant energy. And we've used conservation of energy in other problems back in chapter 5. This is the energy when y is 0. This is the energy when v is 0. These are all the same. That's conservation of energy. So I'm given these quantities, so I can immediately calculate E using this equation. So this equation will give me the energy for the first box, because all the quantities are given. Now I want the maximum velocity. Well, now I use this equation. I just say V max is 2e over m square root. So V max will be the square root of 2e over m. And I calculated E for part A. So now I can calculate V max. Okay, so now you have spring break. These problems will be due after spring break. You've probably already done some of them. They've been open for several days, but anyway, these will be due the Monday after spring break. And then we'll have one more chapter on rotations, and then the second midterm exam. Well, now I should end the recording.